Hello everyone from Math 2000, Linear Algebra. It's Professor Wenson here again with a video on section 1.6 from your ZyBooks titled Gaussian Elimination. So in the previous sections you learned about echelon form and reduced echelon form and pivots and basic variables, free variables, all sorts of stuff, how to express the general solution to a system of equations with infinitely many solutions, and lots of things. In this section, you're going to see how we're going to take just a general system of linear equations, and then through the use of those elementary row operations that we learned about earlier in the chapter, we're going to transform a system of linear equations into a system that's in echelon form. All right, so this section is just on changing it to just plain old echelon form or row echelon form. This is called Gaussian elimination. Okay, so they go over to introduce you to German mathematician Carl Friedrich Gauss, right? Probably one of the most famous mathematicians of all time. Who came up, well, it didn't come up with this algorithm, he didn't come up with this process, but he devised notation for versions of the algorithm. Right? So what you're going to be doing here, you're going to be using Gaussian elimination to solve a system of equations, linear equations. So Gaussian elimination is an algorithm used to solve a system of linear equations. The algorithm consists of what's called forward elimination, and then after forward elimination is complete, you do what's called back substitution. Forward elimination is the process of transforming a matrix that represents a system of linear equations into row echelon form. All right, row echelon form is just the same as plain old echelon form that you've seen before. All right, and on the and I'll show you how to do this on your calculators as well. And row echelon form is labeled REF for row echelon form. All right, so I'll read the steps to you, and then we'll just I'll show you an example. I'll just take the matrix they have here in the first participation activity, and I'll go to a piece of paper and show you how I would put it into row echelon form. So step one is find the current pivot of the first column. The current pivot is the first non-zero entry in a matrix column. If the current pivot is not in the first row, switch the first row with the row that contains the current pivot. So we're going to get the current pivot into the upper left-hand corner of the matrix is what these first two steps are about. Then you're going to perform elementary row operations using the current pivot so that all entries below the current pivot are zeros. Repeat steps 1 through 3 for the submatrix containing all entries below and to the right of the current pivot. Stop when the entries below each pivot are 0. All right. So I'll start off, I'm just going to go to a piece of paper. I'm going to start off with this matrix here, and I might go through these same steps to put it in echelon form, row echelon form. But remember that row echelon form is not unique. So you could see multiple different versions of row echelon form. In fact, I'll also show you on the calculator how the calculator is going to throw maybe a different row echelon form at me. Right, so I'll write this on paper. Okay, so I've written down that same matrix from the participation activity, and I'm going to go through the procedure to put it in row echelon form or just echelon form. All right, so the first step in that algorithm was to find the current pivot of the first column. All right, and it said the current pivot is the first non-zero entry in a matrix column, and this is from the top. All right, so down the first column, that's this entry here, the first non-zero entry. Okay, so this is what they're calling the current pivot. All right, the first non-zero entry from the top of the first column. And if these were all zeros, I would just move over and do it with the second column. Okay. Now that's not in the first row, right? Step 2 was if the current pivot is not in the first row, switch the first row with the row that contains the current pivot. So I'm doing one of those, remember the elementary row operations. Switching rows was one of the elementary row operations. So I'm going to, the current pivot is not in the first row, so I'm going to move it. I'm going to switch row 1 with row 2. Remember the notation for this. This means switch row 1 and row 2. And that creates this this new matrix where now row 2 becomes row 1 for negative 1, 6, 9. And then the first row becomes the second row in this new matrix 0, 1, 2, 7. And the third row wasn't mentioned, right? So 8, 2, 3, negative 5. Okay. So now the current pivot, that number 4, is up here. Right? So here's where my current pivot is. All right, then after this, step 3 was perform elementary row operations using the current pivot so that all entries below the current pivot are zeros. So see the entries below the current pivot. Well, one of them, the second row entry, is already a 0. Great. It's the third row entry that I need to make into 0. So now usually I'd turn these into 1s. Like usually I would, remember another row operation was you could multiply a row by some non-zero number. So like usually I would multiply this row by a quarter just to make this pivot into a 1 instead of a 4. Alright, but I'm going to leave it the way it is because I see that this entry down here, this 8 is a multiple of 4, so it'll be easy to eliminate 8. So I'm going to do what's called zeroing out. Right, we're going to zero out this 8. And that's using the third type of elementary row operation, where you add a multiple of one row to another row, right, and then replace that second row. So what? I'd multiply the first row by negative 2 times the first row, and that would make this negative 8. And then if I add it to 8, that'll make this entry into 0, right? Negative 8 plus 8 is 0. So I do negative 2 times the first row entries. I'm going to add it to the third row entries, row 3, and this will produce a new row 3. Remember, this notation means, replace row 3 with negative 2 times row 1 plus row 3. All right, let's see what we get. So notice I'm only replacing row 3, right? Row 1 and row 2 aren't changing, so I'm going to keep those the way they are. 4, negative 1, 6, 9, 0, 1, 2, 7. It's row 3 that's being replaced that the arrow is pointing to. And I'm replacing it with negative 2 times row 1 plus row 3. So negative 2 times 4 is 8. Negative 8 plus 8 is 0. So what I have done here is I've zeroed out that entry, that third row, first column entry. And now my pivot 4, the current pivot, has zeros below it like I was asked to make, right, like I want. Then again, keep going down. Negative 2 times negative 1 is 2, plus row 3 plus 2 is 4. Then negative 12 plus 3 is negative 9. And then negative 18 plus negative 5 is negative 23. Okay. All right, so now I'm done with that pivot. I got the current pivot, which was at this 4 position here, upper left hand corner, now has zeros all below it. Okay. Then after that it says repeat steps 1 through 3 for the submatrix containing all entries below and to the right of the current pivot. So that submatrix they're talking about is this matrix here. Below, the current pivot was 4. Below and to the right of the current pivot. So now we're talking about this is a submatrix, right? A matrix within a matrix. So I start over with this submatrix. I'm done with that first pivot. So now I look at the first column, right, of this submatrix, just this 2 by 3 down here. And from the top, the first non-zero entry is this 1. So now here, this is the current pivot, the pivot in this step. And that is in the upper left-hand corner. Or it's in the top row, right? We want our current pivot to be in the top row of the matrix we're looking at. This current pivot is in the top row of this submatrix. So I'm good. I don't need to move any rows. Then we use row operations to make all the entries below the current pivot a 0. So I want to turn this 4 into a 0 using some elementary row operations. All right, now this one's already a 1, this current pivot. Again, I like my pivots to be the number 1 personally. It makes it easier to know what to multiply by and then add to other rows to 0 them out. Let's do another operation where, now again, you have the whole matrix. This is the second row. I would have to multiply this by -4. Right? I have to multiply this by -4 and then add it to 4 to make that 4 into a 0. I want to 0 out below. So I'm going to take -4 times row 2. Right? -4 times the second row. And we're talking about the large matrix in general. And then add it to the third row. And this will replace the third row. Let's see what we get. All right. So the first column, I'm only replacing the third row of this whole matrix. So the first 2 rows stay the same. 4, -1, 6, 9. Then second row stays the same. 0, 1, 2, 7. Right. And then I'm taking -4 times the second row entries, adding to the third row entries to get a new third row. Well, this will still be zeros, this first column, right? -4 times 0 plus 0 is all 0. Then -4 times 1 is -4 plus 4 is 0. Right? I zeroed out the third row second column entry. Then -8 plus -9 is -17. And then -28 plus -23 is -51. And there. All right, and now my submatrix is this matrix here, right? Again, the pivot in the last step was this 1, and I've zeroed out all the entries below it, and now the submatrix when I start over is this one, right? Below and to the right of the last pivot. So the current pivot now is this number -17. But, step 5 was stop when the entries below each pivot are 0. All the entries below this first pivot are 0. All the entries below the second pivot are 0. And there are no entries below this pivot, so that we can stop. Right? All the entries between all the pivots are 0. So what I have just done, what I have just performed is called forward elimination, or Gaussian elimination. Right. This last matrix is in what's called row echelon form or just echelon form, and let's double check. All right, let's double check. There's no rows of zeros, so I don't have to worry about that. Where are the leading entries? Right, the leading entries are the pivots here, are the 4, the 1, the -17. You see how they keep moving to the right? Remember, all the leading entries kept moving to the right as you went down the rows. And then every leading entry has zeros below it. This satisfies those 3 properties of echelon form. All right, and you're going to be doing this quite a bit. All right. Now remember, echelon form is not unique. This isn't the only echelon form I could have gotten starting with this matrix. All right. Remember earlier I said I would rather make this pivot, all the pivots I come across, I would make them into one personally. So, if you take any of these rows here and multiply them by a non-zero number, you get another echelon form. If I multiply the second row by 3, you'd have 0, 3, 6, 21. The matrix would still be in echelon form. Let me show you in the calculator too. The calculator might give me a different echelon form. So here's how you use the calculator. All right, so hopefully you recall, if I go to the second, go to the matrix menu, second matrix, and then go to edit to make a matrix, say matrix A. I'll start with the one we began with over here on the paper. I'll start with this 3 by 4. So I got to enter the size 3 by 4, 3 rows, 4 columns, and then enter the entries, right? 0, 1, 2, 7 in the first row. And then 4, -1, 6, and 9 in the second row. 8, 2, 3, and -5 in the third row. Just make sure, double check that you've entered everything correctly. Alright, so now I get out of here after I've entered my matrix entries. I'm going to go back to the matrix menu once I'm in the main calculation matrix, and then over to math. And I've shown you this before. I showed you this in the last video, or 2 videos ago, on echelon forms. If you scroll down, you'll see 2 things that end in REF. There's REF and then RREF. What I have here is row echelon form. That's REF. RREF is reduced row echelon form. So if you recall reduced echelon form in an earlier section, that's what this RREF is. But I want to try REF. So I hit enter on REF, and then in parentheses I got to put the matrix I want to put in row echelon form. So back to the matrix and then enter matrix A, and see what we get. Now you see it's a bunch of decimals here. If you want to change to fractions, go math, change to frac, enter. So there, this is that matrix through use of row operations put into row echelon form. And do you see how that matrix on my calculator looks different? It's got the same structure, right? It's still it's still in that echelon form, like this was zeros in the lower left corner, zeros below the pivots, but all the pivots are 1. So do you see that if you multiplied the first row by a quarter, well, actually, no, you wouldn't get this. Yeah, so this is a total, it's still a valid echelon form, right? Just the calculator did different operations than I did. So it got a different, echelon form is not unique, right? That has been mentioned in a previous section. Echelon form, row echelon form, is not unique. Now in the next section, 1.7, when we talk about getting things into reduced row echelon form, then you'll get exactly the same as what comes up on the calculator, right? All right, so let me get rid of this. All right, so that was an example of Gaussian elimination. Just, move a pivot to the top row of whatever submatrix you're looking at, and then perform row operations to zero out, make zero all the entries below that current pivot, and you keep doing that till you can't do it anymore, until all the pivots have zeros below them, and then you can stop. All right. So again, you can. It looks like those are the exact same steps here. I have the steps up here. Okay. And you have a matrix in echelon form. All right. Okay, so I'm going to write this one up, and let's do the same. All right. Now I know they're not asking they're not asking us what's the matrix in row echelon form, but I'll do the same thing here. Let's take this matrix, and I'm going to perform some operations to put it in row echelon form. Okay, so I've written out that matrix, and I'm going to actually go through and put this into row echelon form. Now the first step is, what's the current pivot? Now the current pivot is 2, but I'm noticing that there's a 1 here. Now again, this is just a personal preference. You don't have to do what I do. As long as you perform valid row operations, right? Switching rows, multiplying rows by numbers, and then taking a multiple of one row, adding it to another row. As long as you perform valid operations, you're good. So what I'm going to do is I'm going to switch these rows. So that way my pivot is the number 1. I like having pivots of 1. It makes things so much easier to do when you're trying to make other entries into 0. So I'm going to switch row 1 with row 2 again. Right? And that leads me to here. Right, so if I do that, that's 1, negative 2, 1, 8 in the first row now. Then 2, negative 1, 2, 10 in the second row, and third row I didn't do anything with. Right. So again, here's my current pivot. All right, this non-zero entry on the top row. All right, this non-zero leading entry on the top row. Now I hope you can see why I changed it so that 1 would be up here. Now I'm going to make these into 0. I want all the entries below the 1, below that pivot, to be a 0. So to make the 2 into a 0, I need to multiply the first row by negative 2. Right, that's why I like having 1 as a pivot, because very easily you can see what you need to multiply by. Multiply that by negative 2 and then add to 2. That would 0 it out. So negative 2 times row 1 plus row 2, and then make a new row 2. Okay. And that gives me this matrix. Right, so the first, I'm only changing row 2, right? The only row that's getting replaced here is row 2. So row 1's the same. Row 3 is the same. It's row 2 that's changing. So I take negative 2 times row 1 entries, add it to the row 2 entries. Negative 2 plus 2 is 0. Then 4 plus negative 1 is 3. Negative 2 plus 2 is 0. And then negative 16 plus 10 is negative 6. Right. Okay, and then one more time, I want to 0 out everything beneath the 1. Right, everything beneath this pivot here. I want that to be the current pivot. So same deal. Since it's a 1, it's very easy. I want to get rid of 3. I'm going to multiply that by negative 3. So negative 3 times row 1, and then add it to row 3 to 0 that out, right? And that creates a new row 3. So only changing row 3 here. So row 1 and 2 are the same. Row 1 and 2 do not change. Alright, then I do negative 3 times the row 1 entries, add to the row 3 entries. Negative 3 plus 3, 0. So now I have what I want, right? All zeros below that first pivot entry that I wanted, below that leading 1. Then 6 plus negative 1 is 5. Negative 3 plus 2 is negative 1. And then negative 24, negative 3 plus 2, right? Yeah. And then negative 24 plus 11, negative 13. Right. Okay. So now I'm done with this, and then the next matrix, the sub matrix I'd be looking at is this one here for my next pivot, because I'm done with this pivot and putting zeros below it. So I go to the below it, to the right of it, and basically the rest of the matrix that doesn't contain that row and that column with the first pivot. Alright, so then my next pivot is just this upper left here, the first non-zero entry down the first column here, 3. Alright, now if there was a 1 below it, I'd switch it, make it 1. In fact, I'm going to make this into a 1 right now. Instead of leaving it at 3, I'm going to make this into a 1 by multiplying the second row by 1/3. Again, the only reason I'm doing this is because I prefer having pivots that are the number 1. Right? So I'm just going to take, negative 1. I'm just going to take 1/3 times row 2. Right, this is the second row, and that'll produce a new row 2. All right, so the only thing I'm changing is row 2. First row and third row aren't changing, so I'm going to rewrite the first row, rewrite the third row, and multiply the second row by 1/3. 0, 1, 0, and -2. All right, so now my little pivot there, my next pivot, is the number 1, which is great. It makes it real easy. I want to zero out the values below that pivot, below that leading 1, which is 5. So I multiply by -5, right? So I'm going to take -5 times the second row and add it to the third row and replace that third row, right? So all I'm replacing is the third row, right? So the first and second row aren't changing, so keep those the way they are. And then I'm taking -5 times the second row entries, adding it to the third row. Well, that's 0 plus 0, 0. -5 plus 5, 0. 0 plus -1, still -1. And then 10 plus -13, -3. And then finally the last pivot, right? This pivot, this leading entry has all zeros below it. This pivot, this leading entry has all zeros below it. And now I'm looking at this submatrix. So the last pivot is this -1, and I'm done because there's nothing below it. So I have finished my elimination, my forward elimination. This is in row echelon form, or just echelon form, or on the calculator REF. Now again, on the calculator, it might give me something different, right? The calculator may have performed operations in a different order than I did to get this echelon form, right? So it might throw out a different echelon form. Echelon forms are not unique for a matrix. Reduced echelon forms are unique, so you will match the calculator when we get to reduced echelon form, but not just echelon form. All right, now that's not what they're asking here. All right, they're asking, all right, which row operation is needed to zero out the entry in row 2, column 1? So row 2, column 1. So if I left it the way this is, right? They're asking me to leave it the way it is. I moved the first row and second row around. I would take, -1/2. Right? If I want to make this 1 into a 0 below the 2 here, I would multiply the top row by -1/2, right? -1/2 times 2 is -1, plus 1 would be 0. So I'd do -1/2 times the first row plus the second row to get a new second row. I hope that makes sense. And they show you what would result. You see the fraction showing up. I mean, I try to do whatever I can to avoid having fractions show up. That's why I like having usually pivots of 1. That's not to say fractions won't show up, right? Fractions will show up at times. You can't avoid it. All right, then, which row operation is needed to zero out the entry in row 3, column 1? So again, you have 2 up here. You want to make this 3 into a 0 using the 2. So I'd have to multiply that by -3/2, right, to turn that into -3 and then add it to 3 to make this into a 0. So -3/2 times row 1 plus the row 3. All right, and they show you that there. All right, and then which row and then you can do the last one. All right. All right. Now, the whole point of this, doing this forward elimination, right, to put a matrix into echelon form or row echelon form, is so that we can solve a system. Right? And we're going to solve a system using what's called back substitution. Right? Back substitution is the process of substituting the value of the last variable into each of the preceding equations right, backwards, proceeding, to obtain the values of the remaining variables. All right, so I'll show you an example here. All right, so they go through blah blah blah. Right, let's say I was trying to solve this system. All right, so I'll write this up on paper, and then we'll make a matrix for it. Now this has the variables, A, B, and C instead of x1, x2, and x3. It doesn't matter. All right, they're still three equations with three variables. All right, so I've written out this system with the A's, the variables A, B, and C, and then the corresponding matrix. Right, you have the coefficients of A down the first column, the coefficients of B in these equations down the second column, the coefficients of C, then an equal sign where the equal signs are, and then the constants. All right. So I'm going to go through and use my forward elimination, Gaussian elimination, and put this into row echelon form, or just echelon form. All right. So again, just as with the last example, technically I would you could use the 9 as the first pivot here, the first non-zero entry down this column, the first column. But I want to move the 1 up here. All right. Again, I like having a pivot of 1. It makes other operations easier to perform later. All right, so I'm going to switch row 1 and row 3. Here's the notation for that. So row 1 is now up top. Well, row 3 is now row 1, is what I'm saying. And then the row 1 on top is now on the bottom. And then row 2 didn't move. Okay. All right, so now I'm working with a pivot of 1. All right, and I would like to zero out the 4 and the 9, right? The numbers below the 1 there. All right, so I'm going to do these both at the same time in the same step instead of one step at a time like in the previous example. So if I wanted to zero out the 4, I would multiply this by -4 and then add it to that, right? So I'd do -4 times row 1, and then I'd add it to row 2, and this would create a new row 2. Right? Also, if I want to zero out the 9, I'd multiply this pivot by -9 and add it to the row 3, right? So I'd do -9 times row 1 afterwards, right? Well, and then add it to row 3 and create a new row 3. So I'm going to create both these new rows. So I'm changing row 2 and row 3. I'm not changing row 1. So row 1 stays the same, 1, 1, 1, little bar where the equal signs are, and then 5. All right, now let's change row 2, with this line. So I do -4 times the row 1 entries plus the row 2 entries and create new row 2 entries. So -4 plus 4, 0. -4 plus -2, -6. -4 plus 1, -3. And then -20 plus 20, 0. All right. Now I'm going to create new row 3 entries by performing this line, where I take -9 times the row 1 entries and add it to the row 3 entries to create a new row 3. So -9 plus 9, 0. -9 plus 3, -6. -9 plus 1, -8. And then -45, right? -9 times 5. -45 plus 25 be -20. All right. So now I'm done with that first pivot, right? The 1 has zeros below it. Great. Next one I'll move to is this. Right? Here's the submatrix I'd be working with, and the pivot, the first pivot, the current pivot is this -6. Now I could turn it into a 1 if I wanted, but I notice all I want to do is zero out the value below it, and they're both the same, so all I need to do is multiply this value here by -1 and then add it to that one. So the next operation is pretty easy. Again, you'll get used to it, hopefully. Do I want to pivot at 1, or does the pivot that I have look good as is? I could just multiply the second row by -1. So -1 times row 2, and then add it to row 3, and that'll zero out that bottom value, third row, second column, and create a new row 3 entry. So I'm only creating a new row 3. So row 1 is the same, row 2 is the same, and now the row 3 changes. So 0 plus 0, 0, 6 plus -6, 0, +3, where I'm multiplying by -1, +3 plus -8, -5, and then 0 plus -20 is -20. This is in echelon form. Right? This is in echelon form right here. I'm done with my forward elimination. Right. Now once I've put it into echelon form, or row echelon form, we can solve for the variables. Right. This is the back substitution that we're going to get to. This system, this matrix corresponds to the following system. Right? Remember the variables were a, b, and c. That first equation is a plus b plus c equals 5. And now this second equation is -6 times b minus 3 times c equals 0. And this third equation is -5 times c equals -20. All right, and then you go backwards. You start from the bottom up. All right, so here comes what we're calling back substitution. Right? Once you've put the matrix in echelon form, you can solve through the use of this. Here again, here's back substitution. So I start at the bottom and work your way back up. Right, work backwards. So we start with -5c equals -20. If I solve that for c, that's c equals 4. All right. Then I use this. I replace c with 4 in all the equations going backwards. So look at the second equation. It's now -6 times b minus 3 times, not c anymore. We know from the last equation now that c equals 4. And this should be equal to 0. And then this is just -6b minus 12 equals 0. And then solving this for b, you would add 12 divided by -6. b would be -2. So now wherever I see a b back in the previous equation, I'm going to replace b with -2. All right, then going back to the first equation, we have a plus b, but b is now we know it's -2, plus, and then c is +4 equals 5. And then this is just a plus 2 equals 5. Solving this for a gives me a equals 3. And so the solution of this system we have found. A is 3, b is -2, c is 4. And that was an example of what's called back substitution. You get the matrix, the system, into echelon form, and then you solve from the bottom equation, substituting as you go back up. And let's test it out. Let's see. Is this really a solution to my original system? Right? Because remember, when you perform all those row operations, you create systems that are row equivalent or equivalent to the original system, meaning they have the same solution. So this solution to that last system should be the same as the solution to the first system. Let's see. Put in 3 for A, -2 for B, and 4 for C. So that'd be 27 minus 6 would be 21, plus 4 would be 25. The first equation holds. Then the second equation, you'd have 12 plus 4 is 16, plus 4 is 20. That holds as well. And then 3 minus 2 is 1, plus 4 is 5. All three equations hold. This is indeed the solution of that system. All right, so you do forward. So Gaussian elimination as a whole. Right, Gaussian elimination is you take your system, you put that system into echelon form, and then you solve through the process of back substitution, right? Starting from the bottom and going backwards, back up. All right, so that's this example there. Now we could do that here. Now look at this. I'm just going to kind of, well, I'll write this out too, right? The echelon, now look at, they've already given me an echelon form here. The echelon form of an augmented matrix that corresponds to a system of linear equations x1, x2, and x3 is the following. What is x3? All right, well, let me pull up again some paper here. Well, I'll just pull it up on the same screen. No, not that. Sorry. Didn't mean to turn the thing off. All right, so now you're seeing some paper. All right. So that matrix right there, the last equation, you know, if remember the first column would be for coefficients of x1, second column for coefficients of x2, and then x3, and then equals, and then constants. That last equation from the last row, 0, 0, 3, negative 9, that's 3x3 equals negative 9. So I solved that bottom equation for x3. x3 would be negative 3. All right, so we have one part of the solution. Then, using negative 3 for x, I go into the second row. The second row, 0, 1, 2 equals negative 4 there. That's 1x2 plus 2 times x3. But, you know, I know what x3 is now. x3 is negative 3 equals negative 4. This is x2 minus 6 equals negative 4. I would add 6. We get x2 equals positive 2. Now I know what x2 and x3 are. Now we go backwards even further to the first row. Now the 3, 1, negative 3, 17 is this equation. 3 times x1, I don't know x1 yet, plus 1x2, but x2 is just the number 2, so I'm replacing x2 with 2. Then minus 3x3, and we know x3 is negative 3, so I'm replacing and substituting negative 3 for x3. Should be equal to 17. So this is 3x1, and then, you know, plus 2, and then plus 9 is plus 11 equals 17. Subtract 11, divide by 3, you're getting x1 equals 2 as well. So 2, 2, negative 3, 2 for x1, 2 for x2, negative 3 for x3 is the solution to this system that this matrix represents. All right, so what is x3? Negative 3. All right. What is x2? 2. All right, and I'm not going to enter the last one. I mean, you can do that. You saw it. And that's exactly what you're doing in these challenge activities. All right. So I'll just speak these out loud a little bit. All right. Let's keep the paper up. All right. So we got, you know, an augmented matrix that corresponds to a system of linear equations. Blah blah blah. Now, look, this is already in echelon form. You can verify that for yourself. So I can, now that it's in, it's in echelon form, I can solve using back substitution. That last row, 0, 1, negative 2, that's x2 equals negative 2. You already know what x2 is. Then the first row, you have negative 2 times x1 plus 4 times x2, but x2 we know is negative 2, and then equals where the bar is, and then 0. This would be minus 8. You'd add 8, divide by negative 2, x1 would be negative 4. All right, and you can double check that would be a solution to that system. So you can move the cursor or whatever up and down, or just actually enter the numbers. But x1 equals negative 4, x2 equals negative 2 for my back substitution. Great. All right, and it looks like, let's see what the next one looks like. There's only 4 of them. Yeah, it's eventually coming here. No, don't jump. Well, I think that's what the rest of it, I mean, it's all Gaussian elimination. So I believe, what do I gotta hit something here? All right, next. I don't know what happened there. All right. All right, so this one you'd have to do yourself. All right. Make this into a matrix with 1, -2 down the first column, -1, 3 down the second column, a bar for where the equal signs are, and then 7, -18. Put it into echelon form, and then solve through back substitution. Now I know you probably know some other ways to solve these, from algebra class, some algebra class you've taken before, but try to practice this Gaussian elimination. All right, this is going to be important, and it's going to help you in the next couple sections too. It's going to help you in the future. All right. So again, I leave that to you, solving systems through Gaussian elimination. All right, and then you have your additional exercises, which again, some of these are part of assignment 2, right, which you're going to be writing out and submitting to me whenever you're done. You can see the solutions here if you wish, but please, please, please try to do the problems before you look at the solutions. You're not going to learn anything if you just look at the solutions and copy them. And there are also some problems that I didn't assign, I think. So please, try doing those as well. And if you have any questions on those, let me know. But you can also view the solutions to those just for extra practice, right? Just to get extra exposure to the material. And that's the only way you get better at anything, is to practice more and more. All right, so that's it for 1.6 Gaussian elimination. Let me know if you have any questions in Canvas, and thank you very much for watching.